Hey there, Year 10 mathematicians, Mr. Herman here, and this skill will be looking at Lesson 3, Scientific Notation, which is from Exercise 3G. The learning goal is to understand that large numbers can also be written in shorthand notation, which I'm going to be showing you, and to also understand significant figures. The success criteria for this is to be able to convert from scientific notation to basic numeral version and vice versa, and to also round a number to a desired significant figure. In order to approach this exercise of scientific notation, we have to backtrack to what a significant figure is. And significant figures are pretty much based on two different types of numbers, whether the number is a whole number or whether the number is a decimal number. It doesn't necessarily work with fractions. And the premise goes like this. The number or the digits within a number hold significance whether it is a zero or a non-zero number. That's pretty much it. With the exception of their positioning as well. So what do I mean by this? Let's have a look at this number. This is a list of whole numbers. This 32 here holds two significant numbers. So right here we have the number 3 and the number 2. Both of these numbers are non-zero. So there are two significant numbers. Excuse me, plain and simple. But then we look at this one here, then we have this number 3, but then any numbers after the 3 that trail on as zeros aren't necessarily significant. So in this case here, the amount of significant figures is only 1, which is this 3. Same with this 400. After the 4, there are trailing zeros that keep going. So there's only one significant number, which is this 4. And again, one significant figure because all of these numbers are 0. But then this changes as soon as there is a non-zero number that is at the end of this digit. So in this case here, every single one of these numbers holds significance. So there's 5 significant numbers. But if that 3 was a 0, again, just like this one and this one, there would only be one significant number. And if there is a 0 afterwards, that concept still applies again, because there's trailing zeros afterwards and it keeps going zeros, so there'll still just be 5. So just like in this example here, all these zeros are considered significant because they're in between two non-zero numbers, but then the 0 after that 3 is considered non-significant. So in this case, it's only 5 significant numbers. And to mean by significant, it just says hold some form of importance to that number, okay? Doesn't mean we just disregard it or get rid of it, but the 4 in these cases here hold some form of significance because it's talking about the magnitude of it. There are 4 lots of 100 or there are 4 lots of 1,000. But as soon as you hit that 3 there, yeah, you can say it does seem somewhat insignificant, but there should be a purpose for that 3 being there. So every single number in between is considered significant. Now the concept kind of changes when it gets to decimal numbers. In this case here, we have got 1.2. Now again, if it's non-zero, they hold significance. So regardless of the decimal point, for this example anyways, there are two significant numbers. Now the concept changes after the decimal point when it comes to 0. So in this case here, we have this 0 that is after the 2, but it's also important to consider that it's also after the decimal point. So any numbers that happen after the decimal point are considered significant with the exception of the last 2, which I'll get to in a second. So in this case here, we have 3 significant figures because this 0 is after this decimal point, and then 1 and 2 are also significant. Same with the concept with zeros in between two significant numbers. All of these digits are considered significant. So there's 4 significant numbers. But this changes when it gets to numbers starting with the number 0 and is a decimal. In this case here, 0 is insignificant. And then any zeros after that 0 is also deemed insignificant. And then the first significant figure starts at that 4 and trails onwards. Excuse me. So in this case here, we have 2 significant figures. Now, again, this concept applies again. We've got 0, which is insignificant, but then it starts with a 5. So we've got this 5 significant, 0 significant because there's a 3 afterwards, when there's also significant, 2 significant, and 0. So in this case, we have 5 significant digits. Now that we're familiar with the concept of significant figures, we're now going to look into the concept of scientific notation. Now, it doesn't have anything to do with science, the topic science. It's just written as scientific notation because it talks about how we can get a big number and pretty much make it easier or digestible to read. So a lot of scientific magazines back in the day didn't like writing numbers that look like this because it was just too big to fit onto the page and a little bit tricky to digest, especially for readers who didn't necessarily have a math or scientific background. So mathematicians found a way of writing scientific notation which pretty much compresses this into a format which is easy to read. Can also look into the magnitude of a certain thing. So say for instance, this might talk about the mass of the sun. I'm just picking something out randomly in kilograms. Obviously too big to read, so we put it into a different concept or a different format. Now, the first thing we have to do is we're going to look for the significant figures. Look for significant figures, which I'm going to just call SF. I'm going to look for significant figures, and in this case here, we have 7 and the 8. So in this case, for this example here, we have 78, which is considered as a significant figure. Okay. And then the second thing we're going to do is with that 78, we're going to change this figure that we have got here, the significant figure. We're going to change this to fit a number, between 0 to 1. 0 to 1. Now these are just the rules that the mathematicians made. In this case here, if I wanted to change this 78 to a number that is between 0 to 1, and by change I don't mean we're just going to turn it into a 7.8 and just leave it like that. What I mean is rewrite it as a starting value like this, 7.8. So this 78, I'm going to say million, trillion potentially, it's such a big figure for me to digest. We're going to start it off as a 7.8. The next thing we are going to do afterwards is if we picture this decimal point here, okay, because this is what we've just turned it into, a number between 0 to 1. Let's picture this decimal point here, which is there. And to the right of this, we're going to count how many figures there are, regardless of whether they're 0 or non-zero. In this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we're going to keep that number aside right now. So what we do is we multiply this by 10. And then however many numbers to the side there are becomes this power for that 10. So the base is 10 and then the power exponent is 13. So this right here is the scientific notation of this. Smaller and a bit easier to digest. And this 13 here, this power, this 13 talks about the magnitude of something. That something is 13 times magnitude higher by 13, okay? So maybe 13 times bigger magnitude-wise, okay? So it's pretty nifty to write it in that format. So I've written this step 3 and step 4 here. You're going to multiply the 7.8 by 10, and then you're going to count the digits after the decimal. In this case, we count a 13, and then this becomes the power for the base 10. Why I've got that arrow there. Now, this also works with negative numbers. The only thing that will be different is that instead of, say for instance, this was negatives 78 trillion, that negative will go here, okay? And that's it. Nothing else changes for the power or the base. Where it gets different is if we look at an example, that has something that looks like this. Okay, I've thrown you guys into the deep end with this example here. It's a decimal number, and when it comes to a decimal number, the rules still apply in regards to writing the first number, but then a few things change when it comes to what you're multiplying it by, and what the power is more specifically. So for now, we're going to look at the significant figures. So we know that all of these zeros are considered insignificant, and then the first significant figure starts at that 5, and it goes to that 8. So we're going to write that number down, but we're going to write it in between a number between 0 and 10. So in this case, this will be 5.643298, because that number is in between 0 to 10. Okay. Then the next rule, apply the multiply by 10. Now, this is when it gets this is when the power that we write here is different. It's actually a negative power, okay? So when we have a decimal number and it starts off with a decimal number, your power for the 10 is a negative. And then what that number is not necessarily, like the previous example where we're counting how many numbers to the right of it there is. In this case, we're gonna count how many zeros there are, including that first 0 there, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's my answer, okay? That's the scientific notation for it. So pretty simple, just different when it comes to negatives, negative powers, it's used with decimals. Positive powers, used with whole figures that are decimal. Okay. Now again, if the actual number itself is negative at the start, then we put a negative in the front there. Okay. That negative power still remains regardless of whether that's a negative or positive, because it is a decimal. All right, we're going to attempt 4 different examples from this, and we're going to change these scientific numbers back to basic numerals and the other way around. Now, changing a scientific notation number to a basic numeral, I find actually trickier than the other process because we're doing a reverse process. There's just a few things you need to consider. The first thing is we know that this number here is going to start with a 5, a 0, a 1, and a 6, okay? Now, I want you to look at how many digits go after the decimal place. There are 3 here. So, what we are going to do is this 3, all right, I'll write this on the side, this 3, I want you to subtract that number from the power that's associated with the 10. Or in other words, what is 5 minus 3? This is 2. Keep this number in mind. The first step that I do, and teachers might show you different processes or different methods, this is what I do. The first thing I do is I write whatever this number is without the decimal. Okay, so 5016 without the decimal. The second thing is I look at this number here, this number that we worked out based on how many numbers there are after the decimal point subtracted to the power. This is 2. This is how many zeros get added to the end of that number. And that's it. That is all there is to it. Because if you were to do this, the reverse process to write this back into a scientific notation, you'll write it as 5.016 because these are the significant figures from here. And then if you pretend the decimal point is here, you count how many numbers there are afterwards, 1, 2, 3, 4, 5, which is the power here. So the reverse process counts how many numbers there are after the decimal point, subtract it from the power, and then add that, whatever that answer is, in this case 2, add that many zeros. In this case here, we have got 3.2 times 10 to the power of -7, and we want to write this as basic numeral, because this power is a 7, negative 7 specifically, we know that it's going to start as a 0 point something. So what I do, again, I write the 3 and the 2. Okay, that's the significant figures. Now, if there's a negative, all I do is whatever this number here is here, 7, I add that many zeros to the start of it. 3, 4, 5, 6, 7. And then lastly, put the decimal point after the first one. And that's your basic numeral. That is all there is to it for this one here. Because again, the backwards process, that's a significant number, which is 3.2. And then we count how many zeros there are. 1, 2, 3, 4, 5, 6, 7 before it. So there's our power negative 7. Last two examples. Write these numbers in scientific notation. Now, here's a little kicker, using 3 significant figures, So the first thing we need to do is, for both of these questions, is we need to convert this digit or this number to 3 significant figures first. So here we have 1, 2, 3, 4, 5 significant figures, but I don't necessarily want 5 significant figures, I want 3. So if there are 3, I'm going to write the first 2 significant figures, which is the 5 and the 2. And then before I write the third one, and this is where we kind of have rounding skills, before I write that third one, I either change that to 1 digit up or keep it the same, dependent on what this number afterwards is, whether it's 5 or higher or whether it's lower than 5. In this case, because it's higher than 5, that 1 turns into a 2. And now that we have our 3 significant figures, the rest, 1, 2, 3, 4 digits, turn into zeros. Okay? So instead of writing 5,218,300, it's just 5,220,000. Okay? So it's kind of like rounding the significance to these figures, okay? Now that we've done that, we can write this in scientific notation. So remember, the steps is first look at the significant figures, 522, write them in, and then change it between a number 0 to 1. Generally, you just put a decimal point after the first number. Then, if we pretend this decimal number here is here, we count how many digits there are after the decimal number. In this case, there's 6, so that becomes our power. Last question, and I'll wrap it up. 0.0042031. Let's first change this into 3 significant numbers. So the 0.00 stays, 4, 2, and 0. So we're going to write the 4, we're going to write the 2, and before we write that 0, we check the next number, see if it's 5 or greater or less than. In this case, it's less than 5. So that 0 stays the same. Now, by default, because it's a decimal number, you would just not include that 0 when that's how we're so used to writing them. In this case, we actually have to keep it. Now, we know that these 3 numbers are significant. So we're going to write 420, put the decimal point there, times that by 10, and then count how many zeros there are before the significant numbers start, including this first 0. Now remember, this is a decimal number, so your power has to be negative. And that's all there is to it. Go ahead, check your log sheet, see what questions you need to do, and I'll see you in the next video.